Welcome back to POE. Today we're going to be talking about moment. This is the first, or part one of a two-part series, and we're going to be discussing something that we've already kind of talked about, but we're going to go into a lot more detail. Moment. The moment of a force is the measure of the tendency of the force to rotate the body upon which it acts. And here is an example. I've kind of used this once or twice in class to try explaining to you what moment is. What I want you to see here is that these two are at right angles to each other. And that's what we're trying to show here, is that we have some type of pivot point. For there to be a moment, there has to be a pivot point, and the distance must be perpendicular to the force. We have the distance is coming out here, this is the lever arm, and the force is being applied down there. Some equations for moment. Moment equals distance times force, and it's very similar to work. We've just been discussing this in some of our previous sets of notes, but that is the equation for moment. The difference here, again, work was distance times force, but they had to be parallel. In this case, moment, they have to be perpendicular. Units. Well, in the SI system, it's Newton meters for moment. And in the English system, it'd be foot-pounds per foot. Foot-pounds per foot. The direction of the rotation is also important. We have counterclockwise is going to be considered positive moment, and then clockwise is negative. That's going to be a little bit counterintuitive for you. We've got some rules that you're going to need to know when you're trying to determine whether or not this is positive or negative moment. This is what we call the right-hand rule, and those of you from physics are pretty accustomed to right-hand rules. They work with a lot of things that we've been doing, and here it's going to work with moment. But if you take your thumb and point it up, and you can wrap your fingers around, and that's the direction that it's twisting, that's positive. If you have to point your thumb down to make your fingers point in the direction you're twisting something, that's going to be negative. If you have your thumb pointing towards you, and your fingers are wrapping in the direction that you're twisting something, that's positive. And if you have it away from you, to have your fingers go in the same direction, that would be negative. Here's some examples. Point towards you. The force is going down, so the fingers are pointing down in this case, and that tells us it's going to be positive. In this case, to have our fingers wrap in the same direction that it's twisting, this would be twisting this way. Our fingers are twisting that way. Your thumb's going with me, that'd be negative. Okay, so let's do some moment calculations. One of the things I want to take you back to is in English, it's foot-pounds per feet. And that means on this very first problem here, they've given us a distance in inches. Well, we're going to have to convert that into feet. So one of the first things I'm going to do here is I'm going to say 9 inches, and I'm going to divide it by 12 inches, and that means that's 0.75 inches. So when I go into my moment equation, and I take the distance times the force, the distance is going to be 0.75, and the force is 20. So my moment here is 3/4 of 20. And my moment is 15 foot-pounds, not per foot. And I have pound-feet. That should actually be foot-pounds per foot. This one's real easy. M equals F times D, and in this case, F is 20, D is 1, so the moment is 20 foot-pounds per feet. Not per feet, I keep using foot-pound feet. Let's get into some little more complicated ones. Now remember, the distance and the force have to be perpendicular. So a lot of people would right away maybe take the force of 20 and say, well, it's being applied 1 foot away, Mr. Kimmel. But that's not the case. It's actually being applied, the perpendicular distance is here. This 20 foot-pounds could be applied right there, and that would only be 3 inches. Well, 3 inches, 3 divided by 12 gives us 0.25. So my moment is going to be 20 times 0.25, all fourth of 20, and my moment is 5 foot-pounds. There we go. Some other moment calculations. We've got a couple different terms here. Ask yourself, what is the perpendicular distance? Well, this could come right down here and be applied at this location, and that would be on that distance. Well, that's 18 inches. 18 divided by 12 is 1.5. So my moment calculation becomes force times distance. The force is 20. The distance is 1.5. So the moment becomes 30 foot-pounds of feet. A foot. That's what I meant. Sorry. Alright. On this problem now, we've got a force that's being applied, but it's being applied at an angle. Alright. In this case, we have a 100 Newton force, but it's coming off at a 50-degree angle. Well, here's my pivot point. So we want to know now, it has to be perpendicular. Well, let's find out how much of this 100 newtons is heading in the y direction. To do that, I've got to find my x and y components. What I've done here is I've used our equation from the other day for the y component. I went ahead and put in 100 in for the force, took the sine of 50 degrees, and we get that force in the y direction of 76.6 newtons. So, what I'm going to do now is go back to my moment. Moment equals force times distance. I now know that the force, the perpendicular force, is 76.6. The distance is 50 centimeters. All right, this is newtons. Now, 50 centimeters equals 0.5 meters. It's 2 spots from centimeters to meters, so it's 1, 2. That becomes 0.5 meters, so I'm going to multiply it by 0.5. The moment then is half of 76.6. And that gives me 38.3 Newton meters. Well, hey, that's the first part here of our notes today on moment. I hope that was informational for you and cleared up moment a little bit. I'll see you on the flip side as we begin part 2.